there's a lot to be learned there. Another local building company, Silver Maple Construction, and then I got into building energy work in 2017. I got certification through the BPI, Building Performance Institute. Um, did a bunch of further training to do airtightness testing and especially large building airtightness testing. So home energy audits and then large like dorm energy audits and multi-fan testing, et cetera. Sort of went down that track. I also installed aero barrier for a while, if anybody's familiar with that. If you come across it, it's a sort of modern, funky air sealing technology. And now, as for a few years, have had my own company doing consulting, air tightness testing, building science education. Just got my HERS Rater certificate. Lots of different activity, all of it centered around building science, building envelopes, building air tightness, thermal imaging, assessments of existing buildings, both like from tiny house up to 40,000 square foot old high school kind of a thing, with modeling of existing envelope assemblies, modeling of change in fuel use if after certain changes are made, helping people make decisions that way. Of course, getting into now to embodied carbon and whether or not it's the best thing to do to just kind of leave things alone. Just constantly in this realm, which is a niche that has a lot going on. Okay, that's about it. Down in the lower right corner, some of the certifications and groups I'm a part of. Also, Vermont Green Building Network. I've been on the board of directors for 3 years now. I know a bunch of Yestermorrow teachers and alum through that board and current other board members. And also ASTM, if you look in the codes, energy codes, both national and internationally in Vermont, you'll find references for all sorts of tests and whatnot to ASTM standards. And so I'm a voting member of the committee EO6, Performance of Buildings, which puts out all the airtightness testing standards, blah, blah, blah. So I'm like way in the weeds of all this stuff. I just want to kind of give you that background. Also, yeah, live right over the mountain, have sort of a small farmstead, got my degree in sustainable agriculture. Um, I keep horses and, hunt a lot and play the banjo and such things. Okay, enough about me, I think. All right. Um, a brief overview of the history of airtightness. And this is as pertains to New England or similar climate or even colder climate buildings. You get too much farther south and things start changing a bit, but we'll keep it here. Okay, so 1700s to 1970s, for hundreds of years, buildings leaked like a sieve. Air quality is fantastic in an old leaky farmhouse, like clean as outdoor air, clean as Vermont air. Durability was great, moisture was never trapped, and heating fuel use was through the roof, literally. 12 cords to heat a farmhouse, maybe 15, who knows, maybe more. Who knows what the kilo BTUs turns out to be. The leakiest house I've ever tested, we'll get into this, was the house I grew up in Bristol, 1860s, like edge of town carriage farmhouse. And it was, for those who know, it was 17, 18 ACH 50. And we'll get into exactly what that means. Anyhow, okay, late 1970s, oil crisis. Let's insulate to lose less heat because we're heating most of these buildings with oil or coal, but usually they had transitioned to oil at that point. So let's trap some heat, let's use less oil, and while we're at it, let's invent a way to measure air tightness. Blower doors were invented basically in 78, 79, 80, right when I was born, right when Yestermorrow was born, 1980. This is all sort of fairly new, although I guess I'm not so sort of fairly new anymore. Um, 80s to 90s, these insulated buildings are getting all sorts of condensation problems, especially that they didn't have, including new construction and renovated old buildings. And we're still losing heat. What was that ACH 50 thing about? What's airtight? Okay. Late 90s, 2010s. Well, air leakage is a primary driver of condensation issues and a huge contributor to heat loss. Okay, we're learning things. Build tight, ventilate right. Have you guys heard that? Anybody heard that phrase? Yeah, it's out there for sure, and it's pretty recent. PHIUS, Passive House Institute of the U.S., requirements are set at less than or equal to 0.6 ACH 50. Again, we'll get into that, but suddenly there are thresholds for airtightness in the standards, in the codes. PHIUS is almost always the most stringent, most effective set of standards that is in existence. They're kind of leading edge. 20 teens to now, tighter is better. Build tight, ventilate right. Okay, we're sticking with that, and that's basically what I'm going to be talking about is right that there, these last 5-10 years, 5 years, 10 years. And now to the future, and this is what I would say a building scientist would boil it all down to in 5 or 10 years, hopefully sooner. They'll say ventilate right first, then build tight, mind your moisture loads, let the assemblies dry out, give people and pets fresh air to breathe, and remember that mechanical systems are only as good as their maintenance over time. Okay, there we are. That's everything I know about the history of airtightness in as small a nutshell as I can put it. Sarah, should I do questions for people in the room or just, okay, great. I think if any, there's a decent amount of time. If any burning questions come up, feel free to ask them. If I know I'm going to get to the answer later, I'll just let you know. Or if it's like, oh, good one, I'll get to it right then. Okay. So the basics of, get myself out of the way here. The basic idea of airtightness testing. This may be total review for some of you, or if you're not familiar with it, it won't be, in which case, great. Here's a building. You put a blower door in the frame. Is my cursor show up? Yeah, sweet. Oh, look at that. Put a blower door assembly in the frame. It's like a canvas, or in the door frame, a canvas shroud with a big fan right here. There's a little reference to going to outside air to inside. Okay. And you use the fan to either blow in or out. In this case, I'm showing out. So you're depressurizing. You're creating a vacuum situation inside the building. At the same time, because of physics and stuff, a corresponding amount of air is going to enter into the building wherever it can, wherever the leaks are. And if there's really no air leaking in, that fan is going to create a total vacuum and the pressure difference is going to go crazy, which doesn't usually happen. There's always some kind of leakage. And so let's measure. The idea is stay hydrated and enunciate. That's the idea. The idea is we can measure the total amount of leakage in the building if we can measure the leakage that's going through the fan because the corresponding amount is coming in through. And so we have this manometer. It's a pressure measuring device that's hooked up. One side input, channel A, you're measuring the pressure inside the house with relation to pressure outside the house. And so that's, okay, great. Input B, pressure inside the fan opening, literally like right inside the shroud here with relation to pressure inside the house. Okay, so what does that do for us? Get myself out the way. Can I? There we go. The size of the fan opening and the pressure difference between the fan housing and the reference, measured by the manometer, are used to calculate airflow through the fan in cubic feet per minute. So we just calculated, quantified airflow. That's step one. And that it takes all that to get to step one. Okay, all these darn fatootin acronyms. Okay, airflow, right? Step one, measure airflow. Cubic feet per minute. Literally, what is the volume of air coming through the fan? Okay, step one. Cubic feet per minute at a certain pressure difference. That's important because the more air flowing through the fan, depending on how leaky the building is, the greater the pressure difference between inside and out. So you got to say, well, there was this much airflow at what pressure difference? And that's how we annotate that. For example, CFM 50 cubic feet per minute at a pressure difference of 50 pascals between inside and out. 50 pascals, you can see it on a blower door. It's like, it's enough you can sort of push on it. It's like, I don't know, not even a bag of water kind of pressure. Not even close to that, actually. It's a fraction of 1 PSI. It's a fraction of 1 atmosphere. But it's enough to accentuate air leaks, and we're going to get into that. It's also 50 pascals is often, or 75 pascals is used as an apples to apples pressure difference. So you can say, regardless of wind and building size and shape, when this building and that building were each at 50 pascals difference inside to out, they leaked this much and that much. And so you can compare. It's sort of how we get through the industry comparing. And then not as important right now, but cubic feet per minute at natural pressure difference, natural pressure difference, because that is changing all the time. Every time the temperature changes, every time the wind blows, every time it's, well, those are two of the most important things. Every time a fan turns on, inside or out, exhaust or supply. So it's always changing. Okay, airflow. Then how do we like give a building a score? How do we say, well, it gets this score? You can say it's so many cubic feet per minute, but how big was the building? That's important because it would be a really different score. So traditionally, residentially, we relate that to volume. Air changes per hour, ACH, everybody's seen that. It's like cubic feet per minute times 60, which is cubic feet per hour divided by the volume. How many times does the total volume of air in the space exchange with outside in one air at a certain pressure difference? And that's sort of how we measure it. ACH at a certain pressure difference, ACH 50. There's a metric that is probably familiar. That's like, we talk in terms of ACH 50, especially for houses. The metrics are changing. We'll get there in a minute. Actually, we'll get there right now. Always commercially and more residentially, instead of using a volume pressure difference or a volume related score, as it were, we're relating the airflow to surface area. And there's something to be said for that being more accurate. It is certainly more accurate when you change form factor. You guys may be talking about form factor, or you will, I bet, which is sort of surface area to volume ratio. And the bigger a building gets, it contains way more volume for much less surface area relative to a tiny house that has a ton of surface area. So when you compare by volume, ACH 50, there's sort of a quote unquote penalty the larger the building gets, or inversely, the smaller the building gets, I should say. When you compare by surface area, it's very, very apples to apples, because you're literally saying per square foot of building envelope that is the air barrier, this many CFM, divide it by that. So, and it's often it's SFBE is usually the acronym, square foot of building envelope. Sometimes SFBE 6, we don't need to specify that anymore. That just means all 6 sides, the 1, 2, 3, 4 walls, the slab, and the lid, whatever the lid looks like. Sometimes it used to be just the 5 sides without the slab. We're done with that. We wised up. It's great. Envelope leakage ratio, one last thing, that is cubic feet per minute per square foot of building envelope. So we're talking multifamily today, so we're actually going to be in the airflow related to surface area, envelope leakage ratio scores instead of ACH 50. Okay, how are we all doing? Cookies, coffee, tea, we're in the weeds. It'll get a little better, and there will be more actual case study picture kind of stuff coming, but that's some background on airtightness testing and measuring. Okay, so we started to be able to quantify airtightness. What have we done with that over time? So this is residential. This is generally using the IECC, which is the International Energy Conservation Code, from which almost all states take their energy code updates. They'll adopt a certain version of the IECC. Maybe they'll make some modifications per the state, but and it's international. We're talking, big time here. Big time, the bigs. Okay, so 26, no target was specified yet, but the air barrier as a concept is even mentioned. 2006. 2009 IECC, no test required, but they mentioned 7 ACH 50 as a threshold. So like, boy, we can do better, but okay, this was 15, 18 years ago, whatever it is. 2012 IECC, you have to test, you have to perform a blower door test. So that was a big change. That was when ACH 50 came into the common building, vocabulary, because a lot more people were testing. And you had to hit 5. 2015, test required, you had to hit 3, and then it hung out there for a while. So Vermont's residential code, the RBs, has been at 3 ACH 50 or less for quite some time. Vermont RB's 2024, you guys may or may not know this, was supposed to go into effect in 2023, got delayed to 2024, got delayed again, rolled out, but without a printed version, was in that status until like a month ago. Governor Scott issued an executive order making it optional, which repealed us back to 2020. Sweet. For a minute, and crazily, as of 2024 code, residential reporting was going to switch to surface area based metrics. We were going to abandon ACH 50, go to CFM 50 per square foot. Now we're back to ACH 50, whatever. That 2.0 is actually an approximation of what it said in CFM 50 per square foot. Meh. Efficiency Vermont has like a certified 3.0 incentive program that came out this version like 2 years ago, I think. And so they were saying 1.0 ACH 50 or less. And then good old Passive House PHIUS, they've been at 0.6 or less for quite some time. Okay, that's residential. Oh yeah. Oh yeah, these are circled because these are optional, especially now optional for the RB's 2024. The others always have been. They either involve some incentive money, perhaps in the case of Efficiency Vermont Certified, also like a nice, good recognition of what you've achieved. And Certified Passive House is optional, but really, really great program and is getting adopted by states, even not quite Vermont yet, but Massachusetts is going there. And it's very comprehensive. I won't get too far into PHIUS. You guys may look at it on your own, but not just performance of the building, but sighting, shading, aspect, direction of glazing, a lot of modeling like that. What else? They're now adopting quickly embodied carbon standards. So like really always on the cutting edge of what is quote unquote the greenest building. Um, okay. Commercial. We'll whip right through this. I have no idea how I'm doing on time. You holler if there's like 20 minutes left. Oh, there's a big old clock right there. Okay. I'm great. All right. So commercial 26 IECC, no test required. They actually mention it's a different metric. We'll switch over to surface area based. So it's CFM cubic feet per minute at 75 pascals difference per surface area of the building envelope, all six sides. Whoops. Voila. Why 75 pascals? Briefly, mostly because the commercial testing standards are designed to be applicable to high-rise buildings, which we don't do much of in Vermont, although we're getting there. In high-rise buildings, you have a crazy huge amount of stack effect, especially if there's much temperature difference inside to out. It's exacerbated. It's a big chimney to the point where you could have natural stack effect if it's a cold day of 10 or 15, 20 pascals. And so 75 pascals tends to overcome more natural stack effect. And there are also, for the commercial testing standards, there are requirements about having a reference pressure at the lowest point inside the building and also having a reference pressure up at the very, very top so that you're making sure that you're actually depressurizing the entire building. Anything 3 stories or under, it's not really required. It's not usually much of an issue. Okay, so 2006, 0.4 CFM 75 per square foot. 2009, weirdly, they stopped mentioning things. Okay, sure. 2012, no test required. They say, but the materials that you use in the air barrier have to have manufacturer's testing at this crazy, 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 crazy low number, 0.004. Sure. The materials are not the problem. It's the seams between the materials that are the problem, just about every time, and the holes in the materials that you drill. Okay, 2015, no test required, but they go back to mentioning 0.4. 2018, test required. That's a big change for commercial construction, similar to residential. All of a sudden, every building is getting tested. The red door of truth, as I like to call the blower door setup, is looking over everybody's shoulder. Incidentally, TEC, which makes the blower door fans that I use, is putting out a red door of truth calendar for 2026, and it's all my like fine art blower door pictures on it. So keep an eye out for that. Okay. 2021 test required, down to 0.25 CFM 75 per square foot. That's where Vermont was about to go. Now it's optional. We're back to 0.3, which is like roughly ish 3 ACH 50. If you're familiar with ACH 50, sure, go there. Efficiency Vermont multifamily high performance 0.08, and good old PHIUS prescriptive path 2024, the lowest on the market is 0.053 CFM 75 per square foot. Okay. Those are the optional ones, and well, and this one now. Okay. Oh, yeah. And so the thing that we're going to be highlighting today, like finally, there's the background, the point of this presentation, multifamily airtightness targets, is this jump between what's required and what folks were getting used to ish, and what is often being spec'd in the case studies that I'm going to show you, which is related to incentives. Sometimes it's efficiency Vermont, sometimes it's national incentives. And it's a big jump. It's like from zero point 0.3 to 0.08, 0.075. And so that's the big squeeze in airtightness specking for multifamily buildings, which equates to basically PHIUS. And this prescriptive path is actually even tighter than like the good old 0.6 ACH 50 equivalent. So, you know, if you get a commercial building to 0.08 CFM 75, it's like 0.05 CFM 50, blah, blah, blah. Okay. So how is this happening? I'm just going to talk about that briefly. Let me go back really like why? And certainly the overview of airtightness is part of the answer, which is like we're in the period of time right now where build tight, ventilate right is a pretty known mantra. And also the modeling of how much heat loss occurs via air leakage is getting better and better. And so we've just been in this like tighter is better, tighter is better. We're already doing mechanical ventilation. We're already doing balanced ERVs or HRVs. We're already doing that. So in that case, you might as well get the building envelope as tight as possible. There's a lot to be said for that. PHIUS has been leading the way. And interestingly, for example, when there's wildfire smoke and the entirety of the outdoor air is the polluted space, basically the only possible way to get out of that is to be in a building that is so airtight that you can super filter the supply air and actually have clean air because there's not anything leaking in through building assemblies. So like passive houses in wildfire smoke areas have been sort of like, cool, we changed our filter more often and it's really nice inside, whereas everybody else is just having to deal with it. So there's a lot to be said about it. And also there's just a direct correlation between air leakage and vapor transport and between air leakage and heat loss. So like, okay, fair enough. Is there such thing as too tight? Hmm. People need to breathe air, building assemblies need to dry. Okay. So like I will say before we get too far into it, any building by code, residentially or commercially, that is at the 2020 levels, either 0.3 or 3.0 ACH 50, has to have mechanical ventilation, balanced mechanical ventilation. An ERV or an HRV, same amount of fresh supply air in coming in as exhaust air is going out. And so you have to build the building that tight. And if it's that tight, it has to have mechanical ventilation. So we're doing that anyway. From that, once that is in place, it's a very easy case to make that there's no such thing as too tight for the building envelope assembly around the mechanical ventilation, because you don't want unwanted leakage. You want to have it all controlled. The irony is we make the building really tight and then we reintroduce big holes in the wall. They're glorified holes in the wall. They have fans on them and they have little heat exchanging cores on them and they recover some, maybe a lot-ish, sort of some of the heat energy that's lost, but you're still taking a really tight building envelope and making it way, way, way less tight. You're just controlling the less tightness. And ironically, the amount of air changes, as it were, that we bring them back to is usually in the 2 to 3 ACH 50 range, or like 0.2 to 0.3. So just like keep that in mind, is that we never get them that tight and then they just stay that tight, because that would be disastrous. We need oxygen. We need to get CO2 out. We need our water to get out, and the building assembly needs to dry. Now that doesn't actually have to do with air tightness, believe it or not, but okay. So many soapboxes. Oh my goodness. How are we all doing? Everybody go like this. Blue blood, yeah, okay. You guys sitting in your chairs on your computers, yay. Whew. Okay. All right. So given all that, oh, okay, so how is this happening? So basically what's happening is educated architects are speccing passive level airtightness for multifamily buildings. It's not a passive house certified multifamily building. You can do that, but these are not, the ones that I'm working with are not. But the airtightness level in particular is way down at passive levels, because it's sort of like, great, the tighter the better. It's a big jump to get from 0.3 to 0.08. And it may come with some incentives, and sometimes they're really worth it. Sometimes it's just sort of the architect was like, awesome, let's go for that. And the builder's like, sure, great, we'll build that. What did we sign up to build? It's like, oh, you signed up for a really tight building envelope. So is it working? Here we go. How do you make it work? And I'm going to talk a lot about BECX, that's Building Enclosure Commissioning. It's sort of it's an industry acronym. It means a very specific thing. It's one of the certifications that I have that I went out to Wisconsin, University of Madison to learn. And it's a whole process education. And then it's also specifically a building envelope, building science component of it. And it's all about, well, you're about to learn what it's all about, but keep an eye out for that phrase. So how do you end up building a large multifamily? And the case studies are 20 to 70 unit, I think, 60 unit, yeah, 20 to 65,000 square foot buildings. Um, how do you do it right? Early involvement of the building enclosure commissioning provider starting at pre-design and/or design phase. 3 tablespoons of that. Willing engagement from the project team. This is the owner that, in this case, it's often a nonprofit developer, Cathedral Square or Evernorth or um, I'm probably forgetting others, but there are a bunch of local regional nonprofits. A lot of this is happening with ARPA money, IRA money. There's a big slug of these projects happening in 3 years. Are they going to be happening? We'll see. But there are a bunch going and more happening right now. So willing engagement from the team, owner, owner's rep, architect, general contractor, project manager, general contractor, site supervisor, subcontractors, everybody's touching the air barrier. The more people sign on to the concept that they agreed to build this that tight, the better it's going to do. Simplicity of shape. Big squares, cubes, long, flat surfaces, not so many funky angles and ins and outs and bumps. We'll get into that more. Again, recipe for success. Um, Packaged product lines, what I mean by that is all of the exterior weather and air barrier components are Huber zip system of some stripe or another, and they're so you know they're all compatible, or Den's glass, so you know they're all compatible. Like one manufacturer, there's more of that being sold, especially at the commercial level, and it helps. Does butyl tape stick to a cementitious surface? Does butyl tape stick well to zip? Does butyl tape stick well to, it's like, okay, yeah. Can they just substitute one tape for another at the last minute? If it's all one product line, I hate to speak like a salesman because I ain't, but that is a thing. Creates additional challenges. Late involvement of commissioning. The earlier the better to spot potential issues, bring them up, catch them before they get repeated 500 times on the building, for sure. Motivation for target is not top down. Yep, I'm just going to keep going. Failure to implement BECX recommendations. Yep. Overhangs, garage podium decks, rooftop penetrations, commercial residential mixed use boundaries, individual versus centralized HVAC for multiple individual units, elevator shafts, stair towers, garbage chutes. It's all stuff that's not usually dealt with in small buildings. I will say, generally speaking, large multifamily buildings are sort of a much easier building envelope because in houses we do angles and we do nooks and crannies and cubbies and unique ideas and soffits and weirdness, and every single thing is awesome, and from a building envelope efficiency and durability and like simplicity of control layers point of view is not helpful. Yes, question. Totally. Great question. Yeah. So in case they're online, you can't hear. The question is, why is it a challenge when there are commercial residential mixed use boundaries? Like specifically, what about that? Different standards apply sometimes. So that's just right off the bat. You might be an ACH 50 on one side and CFM 75 per square foot on the other. And three or five of the surfaces of the square foot of the building envelope are to the outside, but one of those five or two of them are adiabatic, no change in temperature. They're both inside. That does not help. Different, same reason, different building assemblies, often for like fire code. It'll be different on one side than the other. And so they'll have some weird transition where this building envelope goes here and this one goes there, and they're like this, but there's actually a bunch of air movement between them or something like that. Those are probably the biggest two. And then often, especially figuring out how to test, if you have to, are they connected enough that they can be one zone, or do you have to treat them as two separate zones? So I'd say that, mostly that. More kind of paperwork confusion than anything. Um, how are we all doing? Good? Okay. Finally, holy cow, pictures, case studies, real live buildings. Thank goodness. Okay, case study one. And I kept these all as anonymous as I could. The second one you'll see if you, yeah, you could Google Earth it. Sure, do detective work. 24 units, 3 floors, about 26,000 square feet, right here in central Vermont-ish. And it was finished, I think, early this year, early in 2025. Project target, recognize that number. So we are, even though we're multifamily, welcome to my world. If it's 3 floors or less, it falls under the residential building energy standards, and it usually use residential metrics. So that said, we're in square foot of building envelope, but we're at 50 pascals instead of 75. You all know exactly what that means, and so on we go. Target that and this in passive house terms in square foot of building envelope, that is the passive house certification target is 0.05. So that's what they targeted. Final result was 0.018. Now read the decimal points carefully. That is 0.02, slightly under it. So it's one less than, it's a third, a little more than a third of the project target, which means a little more than a third of passive house requirement. So it's like crushing the most stringent requirement. So awesome. It is definitely possible. Yeah, look at that. It's important. We crushed it. It's super airtight. I love my little animations. Yeah, okay. So what did we have going for us? Design stage, building enclosure consulting involvement. I know the guy who did the work. This guy. Here is an excerpt from my design review. I think either I did two. One was at design document stage, and one was at construction document stage. And then when they did IFC document issued for construction, there was like a back check just to make sure it's all up to snuff. And so this is looking at the continuity of the air barrier. They had it marked out, good architects that they are, in this red dotted line right here. That was already on there. Also across here, this is an interesting slab on grade portion of the building. They did not have it connected. They sort of had to go up here, but it didn't do anything right there. It didn't actually get from here to there. And what I've come to learn is that especially when we're shooting for 0.05 way down to passive level targets, that detail gets repeated by the entire lineal feet of the perimeter of the building, which is hundreds and hundreds, and it's going to matter. And so I was like, okay, hey, FYI, I marked it up in yellow and crossed out this and said, and tape it all the way to the zip sheathing. Come all the way from your sheathing layer down and under and around. As you'll see, there were some issues with that. We had to work at it. But that's like the early yellow flag on this detail. That's going to be critical, and it might be hard to execute. And that's a lot of what I do too, is I see that they drew it and they drew a nice dotted red line. Awesome, but can you actually execute that in the field? And will the sequencing be all off to where the insulation goes on first and then you can't access the taping plane? And so you can see why buy-in from the whole project team counts. Because when I'm like, hey, by the way, I know you have 9,000 other details in your head every week. This one's going to matter in a year and a half. They're like, yeah, okay, great. Or they're like, don't want the red door of truth to give us a bad score at the end of it. We're gonna pay attention. Okay, willing engagement from project team. So look at this. Here is said detail. Voila, concrete. Zip our sheathing. We're looking right here. Concrete to zip our sheathing. Whoops. I did a fog test, which I'll show you. It's part of the building enclosure commissioning process. fog was leaking out right here. I did a report, I circled it, I pointed it out. They taped it like this. They didn't actually get all the way to the concrete. Darn it. Um, I wasn't clear enough, sort of. And it's, different than as drawn. Things change a lot. Okay, and so then finally, there we are. They ended up going back over with a new version of Pookie, as Joe Stiebrick likes to call it, just whatever sort of goop is compatible, and they sealed that part. And finally, from pre-design, and this is over the course of a year and a half. Like the first time when I look at it here to when I see that finally done, it's a long time. More BECX stuff going for us. Observation of detailing at air control air components. So I show up at various intervals and look at, is the tape sticking to what it's supposed to? Is it okay to use 3M tape on Advantech? Is it? Is it okay but not warranted? Warranted? Does that matter? Does the project all this is sort of the stuff I talk about, bringing to their attention. We chat through, did the Advantech get wet and is it frozen? And is there any tape that will actually stick to wet frozen Advantech before we have to cover it all with insulation, which is happening tomorrow? I'm like, yep. Doing a super tight building in Vermont. And specifically, all the while, probably the most important part of what I'm up to is keeping an eye on, are we increasing moisture risk, condensation risk? Like it's one thing to not hit a target because there's too much leakage. It's another thing to not hit a target or even hit it, but have leakage in the wrong places to where you rot out the building assembly. So like that's a big part of putting this air barrier in the right place in the assembly. Same thing with the walls. Zip looks good. Is the tape on? Is it lapped correctly? Is Tyvek tape compatible with zip system? Da, 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 et cetera, et cetera. Okay. Pressurized fog testing, sometimes called first instance testing, where I sometimes have to temporarily exclude a unit or a room. Sometimes the sheetrock is already up, put a blower door in, pressurize it, put a bunch of theatrical fog in there, run my disco ball, get the lights going. Tell all the guys on that floor it'll get them high if they happen to breathe it in. No, I don't do that. I don't do that. It's good old theatrical fog. And then go outside and see what's leaking. See where the seams are holding, where they're not. Did we miss anything? Are there any whoopsies and surprises? That's the general idea. And so that's part of the BECX process. So trouble spots when you're trying to do a commercial building, really any building, but this is specific to these large multifamilies at passive house airtightness levels. Window ROs, always. It's always. You get a really nice sequenced, here's how the flashing, what is this called? Updated window air sealing and flashing sequencing detail. Yes, commercial architect, I love you. Is that going to happen? Is it going to work? Is it going to be remembered? Hopefully, if I'm there. Well, we did the first round of fog testing there. I've already got this layer and that stuff and this stuff, but there was, whoops, hang on, not yet. But there was this shim, which may or may not have been accounted for there. And we saw fog leaking at the bottom sill corners. Okay, fine. I said, hey, by the way, this is a different one. You've got these clips here, and also the air barrier actually goes to the window frame. Whoops, because they all want to be able to drain and weep out the bottom, so you can't air seal the bottom from both sides, and da 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 da. So I say, okay, do this. And then I say, oh, we fog tested again, and man, it's still coming out the bottom of the window. A tiny, tiny little bit. This was one of the earliest jobs that I did of this scale that was spec'd to passive house airtightness levels. And so I was like, if I see fog, you fail. I don't know. I'm not sure. I just don't want to see any. So we went after it and we kept going and going. What happens next? Oh, yeah. Look where we ended up. And I was trying to count as I put this presentation together. I think I count 8 separate control layer components in that one picture, and that's only on the inside. Like that's what it looks like when you're chasing this target down its own rabbit hole. And I don't want to say that like broke the bank on the project, but they certainly spent extra hours, and I had a couple extra visits, and there was a lot of extra man and woman labor, person labor on the floor, like on the ground. And often, especially on large commercial projects, the folks who are actually responsible for doing this work, which has been designed, reviewed, and spec'd and talked about in project meetings, are subcontracted out. And they're from, they weren't privy to any of that. And so to get it to translate all the way down through from pre-design down to actually being installed is a whole nother thing. And so anyway, as you can see, holy cow. Um, there's a lot going on there trying to stop this last little bit of air leakage. And again, I didn't have enough experience to know how much is too much or how much is, as you can see, we crushed even the passive house target. So as I've learned, okay, if there's a little bit trickling out at the corners, like we're not going to panic. Um, Other perennial trouble spots at this level of airtightness spec, maybe all the windows, because if you start looking into the NFRC labels or the AMAA standards or the things that the manufacturers say that their windows will promise, often you're going to see this less than or equal to 0.3. Does that look familiar? That's 0.3 CFM per square foot. Is it at 50 pascals? Is it at 75? Good question. Either way, it's a lot more than 0.05 in either metric. And so it's like if you have, 20%, ideally 20 or less, but often 20 or 30% of your building envelope is glazing that is rated to 0.3. Well, then does the rest of the building envelope need to be at 0.0001 in order to compensate? Like there's some interesting questions about what an architect can spec and then what the windows can be. Doesn't seem this is not the sticker from this project. I believe if you dig into the ratings for these windows, they said the same thing, but I think obviously they performed a little better than that. But it was interesting to see that. Okay, yeah, so that versus that. Case study number 2, bigger, 72 units, 5 floors, about 64,000 square feet. Project target is 0.13 CFM 75 per square foot. Where did we come up with that? That is, if you take 0.1 CFM 50, which is a nice round number, which Efficiency Vermont was using for a lot of 3-story buildings, and you apply it and you transfer it to 75 pascals instead of 50, it's basically 0.13 because you're pushing a harder pressure difference. The air actually leaks more. Okay, so fine. Final result was 0.096. So still pretty good. Not a third of the target, but still good. Note it's not passive level. Passive would have to be 0.05 or 0.06, depending on how you look at it. This was 0.09, 0.1 really. So it's still really good, but it's not as tight, but still great. By any metric, that's a really airtight building envelope. So what was in the favor of this one? Simplicity of shape. That's a finished elevation. The big cube. Sweet. No jives, no jukes, no funny angles, no weirdnesses, no overhangs. There is a parking garage, so you can see you can drive under here. So there are stairwells like this portion right there. That's a stairway door. So that's a stairwell, which is the building envelope connects all of a sudden down through. So there's some funny stuff there, but generally speaking, it's a cube. That helps a lot. This is on the roof. It's a flat roof. A lot of these are. We can get into the building science way to do that right, but it's fairly easy on a flat roof if you do it correctly. And same deal, like no attic, no cathedral, no pitching, no venting necessary. All of the insulation is on top of the roof deck. Remember that taped Advantech? That came first, and then they put all the insulation on top of that, rigid, and then they put a big roofing membrane on the whole thing. It's one big flat plane. It's easy to detail, and that's key. And then also you can see these are all heat pumps, so other than these main central air handling units, there's not ventilation in and out of every single room. That's centrally ducted. The heat delivery is hydronic. These are air to water, I believe. Okay. What else? Packaged product lines. I talked about that. So this is a really great example of that. Everything above the podium deck, and interestingly, in this case, everything above commercial standards is zip system. It's all zip sheathing. It's all zip system. They do have a different tape around the windows. It's not zip, but it had to get approved, submitted and approved. And then down here, this is all dense glass element system. There's like sheathing. There's this particular pookie that they put on there. There's the tape that goes with it. And it's all just of a piece. And it's like, yep, it works. And then the question is, how does one interact with the other? Is it okay to join the dense glass system to the zip system? In this case, yes, it's fine. Mostly packaged product lines. Like at some point, you get into the air barrier on the exterior, which wraps into the window RO, meeting the vapor retarder layer, which is not a vapor barrier, it's a smart membrane. It's not the air barrier, it's a vapor throttle to keep vapor out of the wall assemblies, but it has to meet the air barrier. And so how does CertainTeed membrane attach to Den's glass butyl tape? Interesting question. Tyvek tape will do it. What do you know? Okay. More BECX work. This was after a visit saying, yeah, you almost got it, but those clips actually technically have holes in them. Those holes actually lead to the other side of the clip. The other side of the clip leads outside the air barrier system. We're going for pretty tight. And in this case, I would tell them like, it's going to leak a little bit. It's probably not going to bust your threshold. It's up to you guys to decide whether how seriously you want to take it. They'd be like, great. Can we hire a consultant for that? Like, thanks, buddy. I'd be like, well, that's the answer. And so they went for it. As you can see, whoops, hey, there. That's what they ended up doing. They ended up putting more of that stuff on those. Okay. And a beautiful final result. It's crazy. It's funny that I had two fans here. I didn't actually need them. And it is nuts to be testing 60,000 square foot buildings with one fan, the same equipment I use for a house. And it's because at this air tightness level, at these like approaching passive levels, you just don't need to move that much air. And it's also crazy to see that if I put one or two fans in one little corner, I mean, it's a stairway, so it's a sort of a manifold, and I do put a reference pressure all the way up to the top floor over in a corner somewhere, yeah, that little bit of air moving through that one fan has the exact same pressure difference effect all the way up there, especially in a tight building, because there's just not any more incoming leakage. So it's pretty cool. Any questions? That's a great question. How long does the test take to do? So the actual testing portion, like literally gathering the data once it's all set up, 7.5 minutes, maybe. It's like, and I do a multi-point test where I bring the building to -75 and then -6 or 70, 65, 60, gather 7 or 8 data points. Um, the pressure equalization, especially in a fairly tight building, happens essentially at the speed of sound. Sound is air pressure. Movements of air pressure, other than a little bit of friction and sort of replacement airflow, et cetera, is like 5 or 10 seconds, and the fan will have the place. Um, the setup and the preparation, like hours to days, because you to get an accurate result, especially when you're going for super tight, you have to have full control of the entire building envelope. Every single door, window closed to the outside, latched, all the fans turned off, all the dampers closed, nobody opening or closing anything. Um, just that. That's all. That's all you need. But especially at the end of a project when their like punch list is crazy long, they've got all sorts of trades working overtime, they're in there till 7. I often will test at night just to have the place to myself. And it's a lot. And sometimes if, for example, they have individual unit ventilation, and each unit has its own system. Sometimes, depending on the kind of test, I have to artificially mask with tape every single unit's supply and exhaust somehow. So either that's like on a lift outside at every single one of those hoods, which usually doesn't happen. More likely, it's me inside with masking tape on every single grill, every single supply register, every single exhaust register. So, and then at the end of it, go back and take it all back down. So like the actual testing, quick. Um, Quick tangent, two components to the test. One is the quantitative, the other is the qualitative, which is we know how much is leaking, but where. And that I always try to include that. Sometimes it's spec'd in and it's really part of the work, especially in like an assessment of an old existing building. Sometimes I just do it because for all that prep, you might as well gain the information. And that can take a while because that's literally like walking around every corner into every attic space, listening and looking, sometimes using a little smoke pen, fog pen to like try to diagnose what's going on. Um, so yeah, long answer, short question. Good question. Yeah. Question is, when you're testing in the larger buildings, can you feel the leak? Yeah, absolutely. So the cool thing about all this is that all that prep is designed to make it one zone or one balloon, if you will. And so that negative 50 pascal pressure difference or negative 75 is evident at every single surface everywhere in the building all at once. And it's a lot. Like even negative 50, like a normal residential test, you'll like if a window has a little crack or it isn't quite set in the sash right, it'll whistle like crazy, or you'll feel it or you'll hear it. There are ways to set up manometers into different rooms and sort of see which ones are worse, like which ones are more connected to outside. But usually, like, yeah, also, if it's cold enough outside, thermal imaging is awesome because all that cold air coming in, even behind a wall surface, cools it down, and suddenly you have like X-ray vision. You can see studs and stud cavities, and you can see where the squirrels tunneled down into the insulation, and like it's fun. It's kind of cool. But usually, yeah, listening and the 8 million or billion sensors that we have right here for temperature, they're bonkers good. They're really sensitive. And hearing it for sure. Yeah. Oh, and looking. So cobwebs are your best friend. Cobwebs are like the most incredible air leak tell because they're sensitive to just the slightest puff. And so if you look in a basement corner or an attic corner and you see cobwebs and they're hanging still and you're at negative 50 pascals, like, cool, walk away. There's no way there's air moving there. So yeah, those are the high tech tricks of the trade right there. Cobwebs in the back of my hand. Case study 3, when it doesn't quite work out. Okay, so you'll recognize the project target. This was there's a lot that went on here. Final result 0.27. Still under Vermont code, like still totally fine. They got their CO. We had to do some interesting discussion and negotiating about whether or not they got their incentives from Efficiency Vermont and why they didn't hit the target and what was my responsibility and what am I legally liable for as a commissioning provider. Yeah. Okay. For example, if I do a site visit early in the process and say, hey, just a reminder, you have to connect the face of the zip to the face of the concrete. Familiar to anyone? Totally different project, same exact thing. I said, please connect all the way across continuous to there. It's going to be important. Okay. There we are. Done. Nope. Like that's an eighth of an inch gap times 3 inches, 2.5 inches, and it gets repeated 70 times around the building, which then leads through the taped designed air barrier into the stud cavity, which is open to electrical outlets, which is open to chases, which is open to penetrations. It's like, they got the connect it to concrete part, and they did that well, but they didn't continue it to the face of sheathing. So that's that thing about, oops, what did I do? Let's see. Oh, I think I just didn't want to get too far into it not working. So I guess maybe these are the only pictures. What else happened here? This was one where I was brought in after it was already framed and roofed and sheathed, and windows were starting to go in, and they didn't even know that they needed to have an airtightness test for their CO. And so while they were finding that out through Efficiency Vermont, that does outreach and extension and whatnot, Efficiency Vermont also said, hey, by the way, if you hit this airtightness target, here's an incentive. And it was pretty legit. It's like $3,000 per room, so times a bunch. Oh, I didn't put how big this one is. It's right in between the two. It's like 48 rooms and 50,000 square feet-ish. And they said, well, here's the way you do that. You hire a commissioning provider and they wave a magic wand and suddenly you're going to hit a near passive air tightness target. And I was like, hi. It's not exactly how it's supposed to go, but okay. And so we started in, and so it came in late. That was one thing. There wasn't the same top-down buy-in. It wasn't that the owner or architect had said, hey, I know about air tightness. I'm going to spec this. Let's hit it. It was Efficiency Vermont saying, ooh, you need to have a test. You need to hit 0.3. And by the way, if you hit 0.13, we'll give you a bunch of money. And they were like, great, bunch of money sounds awesome. Let's hit 0.13. But it's new. It's still new to some builders for sure. What else happened on this one? More of the same, more like recommendations being pretty explicit and just not being followed, and some really weird sequencing stuff. This one had individual ventilation, so a separate ERV for every single unit with its own intake and exhaust. And at time of testing, they were cramming to get people in, which is always a problem. And at time of testing, those were not all the penetrations for the intake and exhaust were drilled through the plywood layer, but they weren't actually sealed at that level. They were sealed at the inside, but it was still open to the wall cavity. And so there was actually a crazy amount of extra leakage. And the initial test was worse than this. I came back afterward, we did this, but they hadn't, a lot of stuff hadn't gotten addressed. And more specifically, it wasn't designed for that from the beginning. And it wasn't a builder who said, sure, we'll build to that early on. And there was nobody there to say, do you know what you just promised? And here, these details are going to matter a lot. And by the time, so, this is, I think there are two out of probably a dozen that I've done in the last few years, maybe more than that, that didn't meet or exceed the target. So it's certainly the exception, not the rule. And in some ways, because of the simplicity of shape, it's kind of easier in a large multifamily building. You just have to make sure bottom perimeter, top perimeter, where the big flat surfaces join together get sealed properly, or where you punch holes in them. Okay. So, in conclusion, is it worth it? Ramifications of an ultra-tight building envelope include increased risk of high interior moisture levels, especially if mechanical systems don't work well. Just skip down to the last item here on the topic of mechanical systems. It's one thing to have the right number of CFM in and out, which you find an ASHRAE standard, or you can find rules of thumb like we need this many CFM of fresh air per occupant plus square footage. But if you don't pay attention to how those CFMs get distributed and mixed, it may or may not help with things like condensation concerns in the coldest corners of the building, or musty basement corners that happen to have the cat litter in them that just don't ever smell fresh, even though you have plenty of fresh air coming in. So this applies on all scales, but it's especially important in an ultra-tight envelope. Managing overall moisture loads is critical, same idea. And in general, in a modern building, we don't have a dirt basement. We don't have an open stone wall foundation. We don't have like these crazy ground moisture loads. If it's a commercial kitchen with that kind of steam, it's going to have a huge commercial kitchen hood that is like enough to depressurize the entire building to, negative 150 pascals if they actually didn't have makeup air, but that's a tangent. And yeah, these buildings tend to, I think, weirdly, I feel like they have lower moisture loads than single family houses. And I think that's probably just because they always have ventilation baked in. There's multiple floors that are just not even in contact with the ground, or not even in contact with the outside if they're interior rooms. So anyway, but it's super, super important because without mechanical ventilation, that moisture's got nowhere to go. It's not going to leak happily and freely through the assembly like it does in an old farmhouse, or like in an old brick multifamily building from 60 years ago. Pay attention to, I already did that. Benefits, incredibly low heating costs. Yeah, there's a direct correlation between air tightness and heat loss. And so if you have this equivalent air tightness, you just don't have much heat loss, which is amazing. You do have heat loss through your ventilation system, hence ERVs, HRVs. Off we go in that conversation. Occupant comfort, no drafts, no cold corners. That counts a lot. And control of air quality with filtration. That gets back to the wildfire example. If all your air coming in is through where you want it to, and you put a MERV 13 or a MERV 15 or a MERV whatever super high level filter on, you can get fresh, clean air to breathe during wildfire smoke incidents. That's basically the only way to do it. Great. Finally thoughts. That's what that should say. And these are not specific necessarily to large multifamily buildings. These are just like, as a building science guy and former builder, Buildings don't need to breathe. You'll hear this all the time. Buildings need to breathe. There's a great book called Buildings Need to Breathe, or Do They? By Allison Bales. It's an excellent building science book. It's like 3 years old. No, buildings don't need to breathe. People need to breathe. We need oxygen, but building assemblies do need to dry out. Does air need to pass through the building assembly for it to dry out? Nope. It needs to be able to dry freely either to inside or outside. And there needs to be a place where the air leakage stops. So, okay. Ventilate right, build tight. That's my new little crusade, is to flip that mantra around and like stop doing that first and then like adding ventilation as an afterthought. Like fresh air distribution mixing first, moisture load first, then get it nice and tight. Okay, fine. And then this is just like, I guess I put multifamily, but when designing any buildings, this is my, degrees in resource management and sustainable agriculture coming out. But don't forget to consider landscape, habitat, and scale. Then you guys, I mean, Yestermorrow is like, yeah, duh. You guys know. When designing multifamily buildings or any buildings, where we site them matters hugely. And as I like to say, like, what's the difference in habitat displacement between an amazing passive house, certified 2,000 square foot building with a half-mile driveway on a mountainside versus a just poorly built CDX junk box with a half-mile driveway on a mountainside in Vermont? The habitat displacement is exactly the same. Like, you can get into sourcing of materials and sure, like, what's the forestry practices where the wood came from, and like, okay, sure, but the displacement of the habitat where that building is sited, it doesn't matter how efficient it is, it doesn't matter how green it is, it's displacing habitat. So that's my final soapbox, I think. Yay, that's it. Um, we'll leave it there. I don't know. I don't think so. Any questions? The 1,000 yard stairs. Yes, not at all.
So when I studied passive housing, passive design, the goal was to get rid of all mechanical wherever possible.
Yes.
If possible, to have type houses which are also passive in actuality.
Great question. Good to repeat them every time, probably, for the microphone, the questions. Yeah, well, so the question is, there's sort of two parts. One is, as I'm saying passive, is that referring to literally a building that has no mechanical systems, which can function freely on its own without any energy inputs? Um, Let me get to that one first, and then I'll have you remind me the second part. So when I say PHIUS or Passive House Institute certified, that is like a brand name. And that does not mean no mechanical systems. Quite to the contrary, that is like they used the word passive, which is a brilliant move, but it's not the passive that we sometimes think of. It just means certified to this crazy set of design standards with lots of siting, and your mechanical systems have to be really efficient, and it has to be super airtight, all this stuff. Very, very different than the idea of a passive building that is passive in that it functions cleanly and healthily without the input of electricity, without any fans, without any mechanical systems. In some ways, a modern certified passive PHIUS building is the opposite of a passive house. It's like incredibly active and incredibly energy dependent, except you can also just crack the windows and you're still going to have really nice airtight envelope around you. That being said, like, that's the first difference. um, so the second question is, yeah, can a truly passive building that doesn't need mechanical inputs have a tight building envelope? So go back to ACH 50 and that idea of, like, certified passive is 0.6. Vermont code was 3.0 ACH 50. And also that was the line at which Vermont code and the international code says, if it's tighter than 3, you need mechanical ventilation, i.e. you can't have a passively ventilated house. Um, my house that I live in and own right now was built in 1978. Hasn't really been renovated since that time. It tests at like 2.87 ACH 50. I do have bathroom fans. So right there, it's not truly passive. And those help a lot. But I don't have like balanced ventilation or anything. And it's just on the edge of just right. It's basically the total amount of leakage naturally is about what we're trying to recreate with a mechanical system. So there is an argument to be made that like, yeah, if you nail the right at 3 ACH 50 realm, you could have natural ventilation that is provided by stack effect, and you can get little, just like passive vents. They're just little, again, it's a glorified hole in the wall. This one doesn't have a system hooked up to it. It just has like little feathery baffles that as soon as the pressure gets too much, they just open and they just let air in. If you put them down in the basement and put some sort of vent up top, you're going to get stack effect. You're going to get natural movement. It's recreating what the old farmhouses did so easily and naturally, or do, which is plenty of air in through the bottom, through the stone wall, through the whatever, through the basement, through the crawl space, right up through the floor system, right up through the walls, right up through the attic, and then out the vented roof, which we knew how to do 200 years ago or 100 years ago. As soon as we started putting gypsum or plaster in, basically, it's like, whoa, weird. There's all this, there's mold on the roof rafters. Like, I don't know, put some vents in there. And so we knew how to do that. So you can recreate that to some extent. And I think if you do that really carefully, sure. And like, if you air tightness tested the building envelope, it wouldn't test down at the 1 or 0.6 ACH 50, but it would be essentially, when all was said and done, if you then take that super tight one and return the systems back on, you're reintroducing it back to about 3 ACH 50-ish. So yeah, you can do it. You just got to be careful, and you got to understand where the natural draw is, natural stack effect, which is that's free energy. A convection loop will happen wherever you heat one space in relation to another space. Moisture is going to try to move between them, air is going to move between them. And if you use, for example, a chimney, like just on a tangent, I love my tangents. I have till 8. Is that true? We have till 8? Okay, great. We're doing all right. Stack effect, I already talked about it in terms of needing to like have a higher pressure difference for testing large buildings, putting a reference tube up top. The reason revolving doors came into being is that if you try to open a door on a 10 or 15-story building and when it's like 20 degrees outside and it's 60 in the building, the natural stack effect, the warm air in that column, that building column, is less dense, and so it rises. What's really happening is cooler, denser air is pushing in all around and pushing it up, and it's drawing on the bottom because it's trying to replace what's being, the vacuum that's being created. And so if you try to open a regular door on a skyscraper and there's no active like exchange of air, you're pulling against potentially hundreds of pascals of pressure because you're trying to like put a vacuum on the entire building. A revolving door immediately lets the same amount of air out as in. So like, yes, it's an efficient way to get people to go by one another, but we can do that with two doors side by side just as well. It's a pressure equalizing device. So all of that is to say, stack effect is really consistent. It happens because physics, and if you know how to use it, you can draw air into a building. And like, the build tight, ventilate right community is like, duh, don't say this stuff. Like, build tight and then ventilate right. Like, get a system in there. I love it. I think a truly passive building where when the power goes out and your backup goes out and it's, I don't know, 6 months in, still breathes, still gives you fresh air, still dries out is a great idea. So I think you can do it. Often front doors and like entry doors are kind of weirdly a great place, especially underneath. Like they often get a bad rap for being leaky. Like weatherize your door stripping or weather strip your door rising. You know what I'm saying? Um, and that's good. It reduces air leakage, but of all the places for it to leak, like, cool. That's where you sort of expect it. You're already expecting moisture to come in on boots and whatnot. It's a known hole in the building envelope. You don't have to. And so if you get your fresh air under your exterior door sill, and yeah, you might get a little bit of frost in front of your door. Okay, whatever. You get mud and snow in there all the time. That's a fine spot. More important is where does the exhaust air go? It's always going to be pushed up and out. and that's stack effect. And that's why unvented roof assemblies are so dangerous, because in the winter, all this warm, moist air is getting pushed up towards the coldest places. And if it's not vented, if it doesn't have attic vents, gable vents, soffit and ridge vents, some sort of system, it condenses on the underside of the roof, and then we have trouble. Um, but if you know, like, okay, I'm going to put my venting here, I'm going to make sure I control my point sources, make sure I don't have a dirt basement, make sure I have bath fans in the shower that are specifically extracting that like high moisture content separately, just out. Don't even try to let it percolate through the passives. And again, starting to move away from a passive system. Bathrooms are hard because a shower, when it's 10 degrees or 10 below outside, the air in there is just like bonkers hot and moist. And that if that moisture doesn't have anywhere to go, in theory, if you have an amazingly tight building envelope, it'll just stay in solution in the warm air and never get to a cold place. But at some point, you have to exchange pollutants and get fresh air. So when that moisture goes out, at some point, somewhere, it's going to cross a boundary where it gets to surfaces that are too cold. So bathrooms are a little bit hard just because it's like the super point source. Kitchens are the same if there's a lot of open cooking. Those are the two places. I mean, open a window. It's like, it's literally that easy. The reason that, excuse me, the reason that it doesn't get sort of prescribed and talked about and designed is that it relies on occupant behavior, which is both the most powerful tool that we have. Like, we can affect more resource use change with occupant behavior of all of our existing systems than we ever could by replacing every single system right now. Like, done. But good luck. And the other thing is, it can't be relied upon to be 100% consistent based on conditions. You know, if you're relying on a window for your bathroom, you better open the window every time you take a shower. But boy, if you open the window when it's 10 below and you're taking a shower, that gets crazy quick. And like, so it's, big point sources of moisture are the bugaboo in the truly like passively operating house system, but they're not insurmountable by any means. And so again, back to stack effect, if you make sure that where your air is leaking out to allow fresh air to come in wherever it's coming in naturally, as long as when it gets to a cold surface, it either can't stay there, it's not trapped, it gets vented out, or B, it's a surface that's kind of impervious to damage. Like, that's a riskier way to do it, but 80% of the buildings in Vermont have condensation on the underside of some surface when it's 10 below out, and it goes away. It's only when it's sort of this perfect storm of getting trapped, getting deposited, getting trapped, staying there, that's when you get into trouble. So you can do it. It's just, you got to be good with the building science, I would say. Does that answer your question? Ish. Oh, great, great question. Yes, totally. Yep, yep, yep. The question is more about bio-based materials, in a nutshell, and new frameworks is referenced. And I'm a good buddy with Jacob. He and I were on the Jacob Deva Rakusin, who's one of the co-founders and their building science specialist teacher here. I don't know if you guys. They have done a ton of work into first researching and then like normalizing bio-based materials, like straw panels on a larger scale. One of the reasons that's not really in this presentation is this is modern multifamily commercial construction. And it's just like, it's scaled up, it's a whole different realm. And also there's, at least generally speaking, there's less interest and knowledge in what I would call next generation building, which is exactly what you're talking about for so many reasons. Bio-based materials are like carbon sink. They're usually locally sourced. They're, yeah, true carbon sink. They're extracting atmospheric carbon, locking it up in a building. There's a lot of post-secondary consumer stuff. Cellulose is that denim. Denim is just coming out. You can actually get denim insulation at Home Depot. And it's like our 3.5 per inch, and it comes in these rolls, and there's no itchiness whatsoever, and it's like jeans, and it's 80% post-consumer denim, and it's like literally get it at Home Depot in Williston right now. Yeah, they've got it borate treated, same as cellulose. and it's all passes all the same things. Um, so yes, they would. It's hard to scale them up to this scale, those materials at this point, although certain places are doing it. And then I think Massachusetts is amazing because Massachusetts commercial code is what went to PHIUS standards first. And PHIUS standards, always pushing the envelope, are now starting to weight embodied carbon more and more. And so it's going to get scaled up, or it already is getting scaled up. I have gotten a little bit of pushback from Jacob when we were presenting together for saying that I thought bio-based materials were less durable. Um, he's right. It's not about the material, it's about how you treat it and whether it can dry out. I mean, Notre Dame, the wood was there for 700 years till it burned. It's just wood. It's not pressure treated. It's not plasticized. Um, that being said, I have also seen situations, especially with hemp and also with wool, where it was side by side with in the exact same building with a cellulose and Intello assembly, just for some funny design iteration reasons. And when there was a whoopsie with point source moisture and like basically a flood inside the building before it was ready, I saw the bio-based material absorb and hold much more moisture longer than, although I say that cellulose is bio-based too. And it did much better than the hemp. And I couldn't point out why other than it was hemp bats. Well, it was hemp bats and hempcrete, actually. No, I did like literally went as far as to, pull apart assemblies, had a moisture meter, a couple of moisture meters, did moisture testing of the sheathing that was on the cold side of the intellocellulose, and then also on the cold side of the hempcrete, and also on the cold side of hemp bats, which specifically were used in like window ROs in place of fiberglass to kind of like stuff in where they couldn't get hempcrete, basically. Those were the worst. Um, could be related to air leakage at the windows, which was just a conveyor belt for moisture into those particular spots. But the hempcrete was in the same stud cavities as the cellulose, and the sheathing behind it was way wetter. I don't know if it was installed correctly, i.e., what was the moisture content as it went in, and even more importantly, as I've come to learn since, you have to put a backer on, install it, and then if you want to do it, you ought to remove and let it dry to both directions for a specified amount of time before it gets covered up, which is like sequentially, that's crazy to, build a sheathing wall with stud bays, fill it with hempcrete, pull off all the sheathing, let it dry, put the sheathing back on. And so they didn't do that as far as I can tell. So there were but what it told me was it was more susceptible. And again, Jacob, we were presenting and I was sort of on that soapbox and he was like, I really can't stand you saying that because it's really not true. And it's more about how we treat it. And if you do it correctly, these bio-based materials across the board sometimes actually are more resilient. And he made a point, which is true. And I see it with cellulose all the time. It's like, it does better because being bio-based, the cellular structure is used to having water in it, which is a weird thing to say. You can't apply that across the board. Like, don't soak your cellulose every day. But if it absorbs some, okay, and it can breathe it back out. It's not, and even more importantly, when you get into people need to breathe, building assemblies need to dry, any bio-based material is going to have a hard time being a vapor barrier. Sometimes that's a good thing. Sometimes that's a bad thing. If you use that well, it means that dryability is more likely to be maintained in a bio-based material. So like all of these ramifications, but yes, big picture, next gen building, next gen renovations, bio-based is absolutely critical if we think global climate change is a thing.
That's my,
Well, that is currently that is applied regardless of material. And if you get into the weeds of the code, and even more specifically in Vermont, if you get into the code handbook that I think VEIC publishes, which is not the code itself, but it's like a read along. They have a bunch of assemblies and then they have a bunch of chapters on moisture and condensation management. And they will sometimes get into as far as like in an unvented roof assembly, if you're gonna do that, be really careful and make sure that the air barrier is on this side of the insulation. It doesn't say bio-based or not, but it'll say vapor permeable or not. Um, and as I've often tried to think of like, so like the only place I see the need for a true vapor barrier, and like mark my words carefully, I'm not saying vapor throttle, I'm not saying vapor retarder, but a vapor barrier is in the contact with the ground. Everything else can be an air barrier or a vapor throttle, but it should be able to let vapor pass. Um, that said, I have not been able to think of a single true vapor barrier material that you could put in contact with the ground that is bio-based. Okay, magnesium oxide. Okay, you just answered like a 3-year puzzle for me. Interesting. More, there's probably more coming. Plaster, maybe, sort of, not really. What were you gonna say? Yeah. Yes.
Is that snake oil? Who would fit to that? And what kind of efficient thing to apply to these buildings?
Great question. So the question is, there's this stuff on YouTube that looks snake oilish that is aerosolized silicone or aerosolized acrylic. The fog of warm clog, as JLC called it when they first did an article. It's called Aero Barrier. Now it's called AeroSeal Envelope. I installed it for 5 years. I was like one of the guinea pig installers. So yes, I know about it. No, it's not snake oil. It is, and I think we basically ended. Yeah, I'm going to roll with this one. Oh, cool. It's been used here. Okay. The Aero Barrier has been used at Yestermorrow. Awesome. Um, there were only 2 installers in Vermont. Now I think there's only one when I stopped doing it. It is, yeah, it's just that. It's aerosolized acrylic caulking. It's basically DAP painter's caulk, but instead of being gooey in a tube, it's mixed with water, and there's some funny stuff that Tremco does and turns it into a milk-like substance. You run it through little micro mini snowmaking guns, like same exact thing. They've got a high pressure air inlet with 60 psi, and then they've got a little injector cone with a nozzle around it, and the liquid dribbles out, and the air goes whoosh, and it turns it into these tiny, tiny microbeads. Then at the same time as you're filling the space with this clog of acrylic caulking, this fog of warm clog, um, fix a flat for a house is what I like to call it. You, yeah, you're pressurizing with a blower door to 100 pascals. So again, like even for a house, like higher than we test skyscrapers at, like really pushing outward, not pulling in, but pushing air in, so that everywhere that the leaks are is blowing out, and these little microbeads of suspended acrylic travel on the air currents and find their way. And when they hit something at a fast enough speed, they break their surface tension, they start glomming on, they build across. The air pressure keeps pushing, more build up, it bridges, and then it breaks through, and then it bridges again, and finally it builds up enough of a sealant that and all the while you can actually be reading the air tightness as you go because you have a blower door hooked up, so you know like exactly where you're at. Speaking of how could you get a building to exactly the right amount of air tightness, aero barriers weirdly one of the only ways to like dial it in real time. Um, yes, it works. Excuse me, seltzer. Um, it is the same thing as putting acrylic caulking in the cracks. You can do the same thing with an army of workers and 100 tubes of caulking, as long as A, you know where all the leaks are, and B, you can get to them all. And therein lies the magic. So it's like the material is an old thing. We know this stuff. We've been using it all the time. Um, you have to get it driven into the cracks hard enough, hence the 100 pascals pressure, which is like if it holds against that, it's in Vermont, it's going to hold against most natural weather conditions, windstorms we ever see. Um, and it goes where we can't get to, and it seals up, and it's like it's legit. The questions are, for me, how durable is it? Like, great that you measured that when you did it, but and I think the material itself is durable. It's good old acrylic caulking. We know this stuff. It lasts for a while. The kicker is, where does it seal? And if you have a building where the architect said, yep, the air barrier is at exterior sheathing layer, but then you do aero barrier after your drywall goes on, it's going to seal at the smallest gaps first. Like that's just the physics of it because it's building across molecule by molecule. And so 16th of an inch, it'll take half an hour. Once it's all saturated and like up and running, an eighth of an inch, it'll take an hour-ish, and so on and so forth. So if all of your smallest cracks are on the inside sheetrock layer and you do aero barrier, but the architect had it spec'd for the sheathing layer, there may be a little bit of a disconnect about where you sealed versus where it's intended to be. And there might be penetrations where they shouldn't, where they should have been sealed, but they weren't. That's a bit of a thing, especially doing renovations, because often it's like, this room got knocked back to studs, this one still has the plaster on, so the air barrier already is like in and out and in and out, and then you do aero barrier, and it's like, I don't care where, I'm just gonna do the smallest ones first. You're like, great, I don't know where it's sealed, but it's sealed. But it does, and I think the other thing is remembering to put it, ideally, like guide it to sealing in a place that's not gonna get disturbed accidentally. Like if you seal at sheetrock plane, then great, but every time you penetrate it after that, you opened up a hole in the air barrier. So not snake oil. Um, if the whole thing about like smallest leaks first, if, for example, I could go to a building, do a pre-test before I installed, and it said, 5 ACH50, but every gap was a 16th of an inch, I could bring it to passive in an hour because it's like the same as air pressure. As long as you have enough of those little nozzles and enough saturation, it's going to get everywhere. It's going to seal them all quickly and like, boom, done. And like no muss, no fuss, no cleanup.